Just as we decided if an xy ordered pair was a solution to an equation by plugging in for each x and y value and seeing if we had a true equation, we'll do the same thing for linear inequalities. We'll plug in for the x value and the y value, and this time see if we have a true inequality. So in this first equation, when I plug in -1 for x and 1 for y, I'm going to see if I do get a true inequality. So I'm going to take 7 times my x value plus 2 times my y value and see is that greater than -5. So I'm finding this is an xy ordered pair, so I'm doing some substitution here into the inequality. Order of operations tells me I have to do multiplication first, then the addition. -7 plus 2 is -5. So I'm seeing is -5 greater than -5. This is not a true inequality. -5 is equal to -5, and remember, in order to be greater than or equal to, our symbol would need to have a line below it. So since this statement is not true, the ordered pair -1, 1 is not a solution. Now checking in the second inequality, plugging in 3 for x and 10 for y, because these are x, y ordered pairs. So I'm seeing is 10 less than 3 times the x value plus 2. Once again, order of operations tells me I have to do multiplication first, and then I'm seeing is 10 less than 11. That is a true inequality statement, so yes, this is a solution. Just as we graphed equations, we also can graph linear inequalities. Linear inequalities have two variables, so the graph of a linear inequality shows all the xy ordered pairs that satisfy that inequality. Now remember, there are multiple values I can plug into these inequalities because there is an infinite amount of things that can be greater than something or less than something. So in this case, we are going to shade our solutions to show that our solutions continue on in that pattern in a certain direction. If we use an inequality symbol as greater than or less than, we are going to have a dashed line because that ordered pair is not a solution along the line, as you noticed in the first equation of deciding if it was a solution. If we have the or equal to line below it, then we are going to use a solid line to represent that every point along that line is a solution, meaning that every point along this red line, every xy ordered pair would be a solution for this inequality of y is less than or equal to -3/2 x plus 1. So to begin with, we are going to start by graphing the line like we are used to, using slope-intercept form. So remember, this is still following slope-intercept form where -1 is my y-intercept, so I'm going to cross the y-axis at -1. This is showing a slope of 3/2, so I'm going to go up 3 and to the right 2. I'm going to continue on in this pattern until I reach the edges of my graph. I can also go down 3 and to the left 2 because a negative over a negative is also a positive 3/2 slope. Now, since there is no or equal to sign on this inequality, that means every point along that line is not a solution, so I'm going to use a dashed line to represent. Now, to determine which side is shaded for solutions, I'm going to use a test point. The test point you use cannot lie along the line. If possible, use the test point of 0, 0, because it's always easy to plug in 0 into an inequality or an equation. So then I'm going to decide, well, is the point 0, 0 a solution? This is an x, y ordered pair, so I'm going to plug it into my beginning inequality. So I'm going to see, is 0 greater than 3/2 times the x value of 0 minus 1? 0 times 3/2 is 0, and then 0 minus 1 is -1. Is 0 greater than -1? Yes. Since this is true, that means that this point is a solution. Since that is a solution, I'm going to shade that part of my graph. So that means that any point that is in this red shaded area would also be a solution. I could pick any point in that red shaded area and it would be able to plug it into that inequality and I'd have a true inequality. The next example. Once again, I'm going to start by graphing this linear inequality by using the y-intercept of +5 and the slope of -2. -2 over 1 tells me to go down 2 and 1 to the right. This linear inequality has a line below it, so that means that every point along this line is a solution. So then I'm going to use a solid line to connect these points. Then, once again, I'm going to use a test point to decide which side to shade. So I'm going to use a test point 0, 0. I'm allowed to use that because it does not fall along the line. And I'm going to plug it in for x and y into my beginning inequality. So I'm going to see, is 0 greater than or equal to negative 2 times 0 plus 5? Negative 2 times 0 is 0, and 0 plus 5 is 5. So I'm seeing, is 0 greater than or equal to 5? It is not, so that means 0, 0 is not a solution. So then I'm going to shade the opposite side of my line. So that means that every point that lies along that line and every point in the shaded green area following along in that pattern would be a solution to this linear inequality. In this linear inequality, I have a y-intercept of 0, because this is like saying y is less than x plus 0. Remember, that's also like a 1x, so my slope is 1 over 1. So I'm going to continue on in that pattern of going up 1 to the right 1, or down 1 to the left 1. This linear inequality is just less than, so it is not including the points that lie along that line as solutions, so I'm going to use a dashed line. In this linear inequality, I cannot use 0, 0 as a test point because it's on my line. So I'm going to pick a different test point. I'm going to choose the point 0, 4 as my test point this time. So 0 is the x value and 4 is the y value, so I'm going to see, is 4 less than 0? That is not true, so that means my test point is not a solution, so I'm going to shade the opposite side of my dashed line. So to sum up what we've now talked about on how to graph a linear inequality, we have the steps below. If you'd like to pause and put these in your notes, that would be a great idea.